Hello everybody and welcome to NPTEL online certification course on cryogenic electronics for quantum computing. This is lecture number 28 and we will look into the device performance modeling at cryogenic temperatures, right. Now, we will start from where we left in the previous lecture and we will look into the Poisson-Boltzmann equation, surface electric fields, we will look into the derivation of charge densities, primarily fixed charge, mobile charge and interface trap charges. What are fixed charges? Let me give you an idea. So, typically if you would have studied, let us look from first principles. If you have studied Gauss law, you already know that Gauss law relates to electric field with the net charge within a Gaussian surface, right. So, charge and electric field are related to each other. The way we had moved forward, if you remember in the Gauss law, if this is the Gaussian surface which you have, if you have positive charges which are 4 in number, let us suppose, then there will be electric field which will be originating from these charges and it will be directed to perpendicularly from the Gaussian surface in the outside part. So, this electric field can be related to the number of charges inside the Gaussian surface. Now, let me take another option and we say to that this is the Gaussian surface, but there are 3 positive and let us say there are 3 negative charges available here. Then the electric field will all terminate within the Gaussian surface, and since the net charge in this case, net charge is equals to 0, I will have electric field equals to 0. In this, since the net charge is 3, let us suppose, then there will be a non-zero electric field available to you. So, the methodology when we do a device modeling, be it cryo or at room, we try to find out the net number of charges available in the region of interest, and then we extract the electric field. And so, there are 2 ways of doing it. One is you find the potential, find the electric field, extract the charge, see the current, right. That is how generally the modeling is done in the domain of semiconductors. But to understand that, we also need to understand the various contribution of charges, and the various contribution of charges are, you have a fixed charge, mobile charge and interface charge. Fixed charges are charges which are fixed in the lattice, mobile charges which is moving within the lattice by application of an electric field, and interface trap charges are the charges which are actually at the silicon dioxide interface. So, this is at silicon dioxide interface, and these are mobile charges which are basically the contributing into the charge, and these are fixed charges we define as QF. So, the total charge is QF plus QM plus interface charge density, right. So, let us take up one by one and we apply a 1D Poisson. When I say 1D, I mean to say one dimensional Poisson equation. One dimensional means it is in the y direction. Please keep y direction as the transverse direction, as I have shown in the previous lecture. What does it tells me is that it tells me that del of del y, right, and this will be nothing but del, as I discussed with you, del psi of del y will be some function here. So, this is basically del E of y del y will be equals to minus q by epsilon silicon and so on and so forth, where psi is the generalized potential, VCH is the channel potential, UT is basically KT by Q, which is the thermal voltage here, remember. This Ni is my intrinsic carrier concentration, this is my intrinsic carrier concentration, right. This is the acceptor ion concentration. At this stage, not saying that whether this will be ionized, fully ionized, degenerate, non-degenerate, do not worry about it. Ni is the intrinsic carrier concentration, psi is the potential, right, generalized potential, VCH is basically my channel potential, right, channel potential, and UT is already defined here as KT by Q, which is basically my thermal voltage. So, you see on the left hand side here, when how the electric field varies with respect to space is related on the right hand side with the total amount of charge available, right, and this is my rho value. So, it is basically the number of charges which are available. When you multiply it with Q, you get the total charge. So, that is what the 1D Poisson equation is all about. 1D Poisson equation we are saying because we are trying to find out the variation along the transverse direction. When your channels are very short or very short, you also need to keep in mind that the variation will be there from source to drain as well. That will give rise to 2-dimensional Poisson equation. Now, a 1-dimensional Poisson equation is sufficient to at least start with the basic idea of the device part in a generalized sense. Now, if you look at the intrinsic carrier concentration, we already know it is Ni is equals to NC NV exponential minus Eg by 2 kT, where Eg is the band gap, right. This is basically your Ni square. So, I get NC NV as the effective density of states in the conduction and valence band. Now, you know that NC NV, so what is the critical part here is, the critical part which you as a designer should know is that NC is basically the conduction band effective density of states, and NV is the valence band effective density of state. Density of states is number of states per unit volume per unit energy. So, if within 1 electron volt how many states are available, right. What happens is, if you go in the conduction band and as you go higher and higher in energy, the density of state becomes more and more, right. So, the difference between two energy states actually reduces when you go to a much higher energy states. That happens both in the conduction band as well as in the valence band. Valence band is you go down, and in the conduction band as you go up, the density of states becomes much more dense. So, the difference between two energy states actually reduces. We have already seen in our previous discussion that this Eg part, which is the band gap, this is my band gap actually, this is my band gap here. This band gap, if you remember, is a function of temperature, and this we had derived earlier through Varshini's model. So, through the Varshini's model, we already know that the band gap is a true function of temperature, right, and it can vary with temperature. So, let us look at the importance of intrinsic carrier concentration, which we already did in the previous years. We will quickly go through it. So, at even a deep cryogenic temperature, Ni remains a small but a finite value. So, it is small, but nonetheless it has got a finite value. It is not a zero value, right, it has got a finite value which is there. Now, there is a catch here, there is a small amount of discrepancy in our understanding that what happens when we log our temperature to 0 Kelvin, right. Then we say that Ni equals to 0, or there are no intrinsic carrier concentration at 0 Kelvin, right. However, this is intrinsically I should say goes beyond the principles of physics. The reason is, at 0 Kelvin, if I assume that my intrinsic carrier concentration is 0, this would actually imply that there are no mobile charge carriers available even at 0 Kelvin, right. But that is not true. There will be some mobile charges available to you by virtue of doping concentration. That is the reason you see the last point which is mentioned in the slide, that this contradicts the observed field effect and MOS transistor operation at 3 Kelvin. So, what you observe physically at 4.2 Kelvin and what you model, there is a small variation at 4.2 Kelvin for a MOS device, simple MOS device, and these are when we are talking about bulk MOS device as well, nothing extraordinarily difficult. So, we remember KT by Q is UT, but what happens is that the exponential factor in the equation has a large dynamic change. I will show you which expression. Let us look at this expression here. This is basically an exponential dependence on psi, right, and this is also an exponential dependency on psi. Psi is the potential. So, if my psi changes by small amount because of cryogenic or whatever reasons, the change in the quantity, this quantity becomes excessively large, right. So, that is what I have written here. The exponential factor in the equation, right, has a large dynamic range when psi changes. So, when psi changes by even maybe 5%, the overall number of charge changes by a drastically large effect, and therefore, this dominates over Ni, and therefore, the MOS transistor operation is significantly affected. So, there are two factors which is happening. One is a temperature dependent UT. So, if my temperature falls down to a very low value, my KT by Q will also fall down. But where is my KT by Q? It is somewhere in the denominator here. If you look at this UT, it is KT by Q. Now, if your temperature falls down drastically, UT will fall down drastically, which effectively means that this quantity will be relatively large, right. So, at low temperature, and that is what I was trying to focus to you in a much more detailed manner. So, what happens is that at 300 Kelvin, UT is approximately 25 millivolt, and when I actually slide it down to around 4 Kelvin or 10 Kelvin, this quantity which is psi minus VCH by UT will show an excessive increase. So, and since it is exponential one, even a small change in psi s will change the value of your total number of charges. So, the sensitivity to the variation of UT is and to the psi is very prominent at very low temperatures in a sense. So, that is what I have highlighted in this slide. Now let us come to the electric field, because electric field is an important property or an important sort of a parameter which you need to understand when you design cryogenic. So we have just now, I am just replicating the same expression here, that d2 side dy2 is equals to minus q by epsilon into this quantity here. Now if you multiply by both equation on the both sides and do some manipulation, I get this expression into consideration, and I get on the right hand side this, where Ga is my degeneracy, right. For all practical purpose, if the degeneracy is 0, I will never have a degeneracy, and when Ga equals to 0, this quantity vanishes, right, and you are only left with Na, which is the original sense, right. So what you will do, you want to find the electric field at the surface, right. So what you do is that you try to find out the electric field, and you do it by differentiating the potential with respect to y. So so if you remember correctly, if this is my source and this is my drain, this is x actually and this is y, right. So when you do d psi dy, right, d psi dy, it actually tells me the value of Ey. Ey is electric field in the transverse direction. However, please understand that at the edge of the depletion, my Eb will be equals to 0, electric field will be equals to 0. I hope you understand this point, that as you go from top to bottom, near the substrate edge where you have a depletion region, my Eb will be always equals to 0, right. And that is the reason it is written here that integrating from bulk to surface with E equals to d psi dy and Eb equals to 0. This is the bulk. At the bulk, the value of electric field will be 0, where it integrates with that of the surface potential. And this leads to Es square, the surface electric field, Es square to be this, looks like a complicated quantity which comes out to be something like this. So if you want to find out the Es, there will be a square root term which will be available here, and that will give you the value of electric field. Now what we are trying to do here is, we are trying to bring in the field assisted ionization of the dopant species. Till now we were assuming, when we are doing Poisson equation solution for one dimension, we were all assuming that 100% ionization has happened. Now let us say I have a field assisted ionization being generated, and this can be directly implanted into our electric field. So what we do, rather than Na, we replace it by a term which is given by this quantity, right. And I am not going to details of this one to a larger extent, but this is how semiconductor design takes care of, right, where psi is the overall channel, Vch is again the potential of the channel, psi a is the potential where the acceptor ions are placed, and so on and so forth. And therefore this leads to an electric field which is basically of the square term. So I get Es square in this domain. Now if I further go and do a routine calculation, I get the electric field term to be this much. This is the electric field term, and it depends upon many factors, but primarily it depends upon the surface potential, the bulk potential, and it also depends exponentially on the value of your channel potential and your surface potential, right, or surface and bulk potential in all the cases. So I say psi b to be equals to EFB minus EI. EFB is the Fermi level at the bulk minus the intrinsic Fermi level, and if we divide by Q, I get the potential in that direction. Similarly, surface potential, I will get the Fermi level at the surface minus EI. EI is the intrinsic Fermi level, it divide by Q, which you get, right. What is EFB? This EFB is denote the Fermi level at the bulk, and this is the Fermi level at the surface. Surface means at the silicon dioxide interface. And what is EFB? Exactly at the bulk which you see. Now the interesting part therefore now comes into the picture, that the logarithmic term in the contribution of the incomplete ionization, where this is the incomplete ionization picture, right. This is the incomplete ionization picture which you get, that 1 plus Ga, G suffix a actually, e to the power this thing, kt, k is small here, is equals to this quantity. F of Ea is this quantity. Where does the incomplete ionization comes into picture? This factor enters the incomplete ionization. Had it been fully complete ionization, everything was fine, Ga would have been 0, and the quantity Fs of Ea would be actually equals to 1, and we wouldn't have taken too much amount of modeling exercises to find the value of Fs of E. Similarly, if you look at F, this is Fs of Ea. This means the surface potential because of acceptor ion, and this is the bulk potential which comes out to be this, right. The Fermi level at surface potential, it depends upon the value of your surface potential here, and if you look at Fb, it depends upon the bulk potential here, right, where Fb is the Fermi-Dirac ionization probability in the bulk, and I am assuming that the channel potential is 0 in the bulk, obviously because it is the edge of the depletion which will happen, right. So, these two factors come into picture. Now, let us go through the derivation of charge densities. We very well know through Gauss law that the total charge is given by epsilon times Es, where Es is the electric field. Now, at 77 K and 4.2 K, an interesting phenomena occurs, that somewhere around if you are plotting this is on the left hand side, you have this charge QSC is the charge, and you are plotting with respect to psi s minus VCH. Psi s is the surface potential and VCS is the channel potential, right. This is the point where psi s and channel potential is exactly the same, and somewhere here around 0.6 the difference becomes approximately equals to 0.6, the difference between the surface potential and the channel potential, and suddenly the charge increases. Why the charge increases? Very simple and straightforward, because you have crossed the threshold and suddenly the inversion takes place and the charge shoots up, right, and that is what is happening, out of which the red colored line is basically the 300 Kelvin line, and 4.2 Kelvin and 77 Kelvin are given in this manner. Now, if you look very carefully, when you are not in the inversion region but before the inversion region, your dotted line which you see, which is primarily 4.2 Kelvin here, shows you a larger sort of a charge distribution. But once you reach to the post inversion, the current contribution because of 300 Kelvin is relatively much larger as compared to 4.2 and 77 K, right, and this is known as the transition or a crossover. So, you see this crossover taking place here. Initially this red colored was below the blue, after this the red colored is excessively larger as compared to the green, and therefore the rate of increase is also larger. Not only that, the absolute value is also very larger, and this transition occurs when the acceptor ion concentration bends under the Fermi level EF at the surface. So, when the EA goes below EF, you have a certain bending and psi s becomes much negative as compared to psi of A. Now, at room temperature, EF lies above EA, but obvious it is somewhere between EF and EA. EF is between EA and EV, valence band conduction shift. So, typically there are no kinks. So, this is what we define as a kink here, right. This is we define as a kink here. Similarly, this is a kink here, right. Now, because of incomplete ionization, which is not visible at 300 Kelvin but visible at 4.2 and 77 Kelvin, there is a small kink in the voltage at the transition, right. Now, when the ionization is complete, in which the case this one is the complete ionization here, this is complete ionization, right, and this is incomplete. In incomplete you see a kink, in complete you do not see a kink, right. It is almost a smooth transition which takes place, and this is because of the incomplete ionization in a sense, right. The kink is basically in the charge. Now, if you have a complete ionization, why don't you see a kink is there is a very regular increase in the charge with respect to potential, but when you do an incomplete ionization at certain value of critical voltage, there is sudden excess because of electric field assisted ionization that adds suddenly to a value, and therefore there is a discontinuity in the carrier concentration. We do not have to go into details of this, but this gives you the fixed charge based on charge sheet approximation and full depletion, gives you a charge sheet approximation, and as you can see is a function of the difference of the surface potential and the bulk potential to a larger extent, right. And the same expression which we saw earlier, now we are doing the fixed charge with respect to psi s minus psi f. So, that was a mobile charge, now we are doing fixed charge for both incomplete as well as for complete ionization, and we are keeping the acceptor ion concentration to 10 to the power 18 in a sense, right. Now, the fixed charge density at room temperature, which is the red line here, this is my complete and this is my incomplete ionization, and for liquid helium we take 4.2 Kelvin, which is the blue colored line, and liquid nitrogen is basically the green colored line which is there, and this includes both complete as well as incomplete ionization. Here also you do not see a very heavy kink effect for fixed charges, because there are certain reasons for that, we will not go into details of it, but typically we do not see a large amount of difference in the fixed charge. Let me come to the mobile charge. Mobile charge is basically if you take the total charge and subtract the fixed charges, you will get the mobile charge, and if you subtract it, I get this expression into consideration. And typically what we have seen is that incomplete ionization does not affect the turn on rate of the mobile charges. However, it tries to slight decrease in the charge threshold is maintained, right. Charge threshold is that charge potential at which you will go from accumulation to inversion region, that shifts slightly to the right or slightly increases. Let me come to the interface trap charges. As I discussed with you, these are formed because at the interface of silicon dioxide and silicon there are certain unbalanced bonds available, and they end up having interface trap charges. They happen because of structural defects, because of lattice imperfections and disruptions at the oxide semiconductor interface, right? This basically happens at the oxide semiconductor interface, and therefore these tend to weaken the gate voltage over the channel. So higher the interface trap charges you have, less control the gate will have over the channel, and therefore the process which you do in formulating a MOS device should be very proper to keep the minimum value of the charge. Now we need to look into the value of the mobile charges at 4.2 Kelvin, and how does it affect the overall principle here. So if you look at the surface boundary conditions, I say that gate voltage can be broken down into flat band voltage because of the metal semiconductor flat band, plus Cox times epsilon into Es into psi s minus psi b. Psi s minus psi b is basically the difference between the surface and the bulk. If you add that with the total charge multiplied by Es at the interface plus the flat band voltage, because metal semiconductor flat band and MOS, if you add those three, you should ideally get the value of VGB, which is gate to bulk voltage. This is basically the surface boundary condition which you see. Now, so the interface trap charges, if you look carefully, they represent the charge density associated with interface traps. So it is charge per unit area, you can find out per unit energy state. Now there can be acceptor type, there can be donor type of traps which is occurring, and these are very temperature dependent. Now if the temperature is very high and if it is very low, then the trapping probability actually changes with respect to temperature. When you switch on the NMOS device, all the donor states actually remain in occupied and neutral, right. So what are the donor states? Which have donated one electron, right. Now they have not donated at turn on phase. When the gate voltage switches on more than the threshold voltage, my donor states remains occupied. I can give you a reference later on, but there is a big sort of assignments available where the trap energy and assigned densities are related to each other, and it is related how the traps are located in the band gap, and its corresponding charge can also be correlated in this sense, right. So this is the final expression which we get for the Fermi level. I will not go into details of that, but I will give you assignments on this, maybe have a look into it, and this gives me the level of the traps. Now basically the Fermi-Dirac occupation probability of the trap at the trap energy level, right, and that is an expression which is depending on the value of psi s and to a larger extent, right. So let me recapitulate what we did for this half an hour lecture. We tried to find out the basic modeling mechanisms, right. So we looked into basic modeling scheme here, right. We looked into the modeling scheme, we looked into the Poisson equation, and we tried to make some corrections in the Poisson equation with respect to electric field and surface potential psi s. There is also a term known as VCH. There is also a term which is psi of xy. We then finally ended up looking into traps. So we divided the charge into mobile charges, we looked into the fixed charges, and we looked into the interface trap charges. And all these three are related to the electric field which is available to us in the device itself. With this, we have been able to at least see which quantity within the Poisson equation affects the overall characteristics of the device to a larger extent, right. So I think you enjoyed this topic. We will have assignments on this as we move ahead, and I hope we will meet next time with another topic related to the modeling scheme. Thank you very much.